Welcome. This talk will be about GPU passthrough and playing video game in Cube operating system. About myself, I am using Cube for around 5 years and playing video game on it for the same amount of times. I am using it for everything, playing game, running server, reverse engineering, and offensive security. Why do I want to play game on CubeOS? I don't want to buy multiple very expensive computer for multiple use cases. I want to have one computer using CubeOS as my only operating system and be able to do everything I want to do on it. Before we start the main course, a quick reminder of the name and acronym we will be using in this presentation. Xen, a hypervisor, something that can create virtual machine. DOM0, the Xen administration virtual machine used to send order to Xen. DOMU, a virtual machine that is not DOM0. HVM, a type of virtual machine. PCI, a way of connecting hardware to a motherboard. And finally, Xorg, software responsible for display for Linux. So what is GPU passthrough? The basic idea is that Xen access to the hardware, in your case, the graphical card. And we want to configure Cube so that Xen assigns the graphical card to a virtual machine. So that only this virtual machine will be able to use the graphical card. So now that we have the basic down, we can move to the summary of this presentation. First of all, we are going to talk about the evolution of the difficulty of configuring this GPU passthrough. Next, we will look at 2 bugs that have affected this graphical card assignment. And in the end, we are going to revisit the wish that the user Deeplow had and how easy to use GPU passthrough can be. For the last 5 years, I maintain a guide that explains what you need to do to properly configure GPU passthrough to play video games. First of all, we were able to solve a bug in Xen. Solving this bug allowed us to delete a whole section of the guide. This section was the hardest part of the guide and required voodoo magic that no one actually understood. We also found a simpler way to have a working audio in a gaming virtual machine. No need to configure Xorg anymore. And we went from multiple pages of documentation to 5 lines of code. Also, Nvidia modified its view on virtual machine. Before, Nvidia wanted people to buy professional card to be able to use it in a virtual machine. So the Nvidia driver checked it was running in the virtual machine, and if it was the case, it killed itself. So that's not the case anymore. So let's try to dive into the first bug. 2 conditions for the virtual machine to crash. First, assign more than 2 GB of memory. And last, configure GPU passthrough for this virtual machine. Back in 2018, the user Al Creator found a workaround to be able to assign as much memory we wanted without crashing the virtual machine. It was about configuring the parameter max RAM below 4 GB. To simplify things as much as possible, the address space of a system is composed of multiple things. Random access memory is one of those components, and a way to communicate with the GPU is another one of those components. So that's how we understood it. If the other thing plus random access memory plus PCI was smaller than what we can store in a 32-byte address space, it worked. If the other thing plus random access memory plus PCI was bigger than what we can store in a 32-byte address space, it crashed. So we use the parameter max RAM below 4 GB to tell the system how much random access memory it can try to fit in the 32-byte address space before assigning the remaining random access memory into the 64-byte address space. The workaround actually worked only with a very specific value of 3.5. For example, 3.4 didn't work and 3.6 didn't work either. The very specific value that you need to use is in fact either 3.5 or 2, or maybe other possible value depending on BIOS configuration. So we have to go deeper to understand what is going on. Back in 2022, the user Mati sent a patch to try to fix this issue. When I started to try to understand the issue, I got very interested in a code comment in this patch, as we see in this slide. The HVM loader is trashing the guest memory. So let's see the Xen source code about this HVM loader fix. We see a parameter used to configure if we should allow memory relocation. What we call QEMU traditional is a fork of QEMU that has been used by Xen. It is decade old and not maintained. QEMU Xen is a modern and maintained way of using QEMU in Xen. TubeOS use QEMU Xen. And here we have the description of our bug. There is a difference in functionality between QEMU traditional and QEMU Xen. QEMU Xen is not able to relocate memory properly. So this is my understanding of the issue. When Xen is sending two blocks of memory that overlaps to QEMU traditional move what is required to have a working guest memory. However, QEMU Xen is not able to do that. It just trashes the guest memory with a big splash sound when the two blocks of memory collide. So the solution is to be sure that the Xen parameter allow memory relocate is set to false. So Xen don't give two overlapping memory blocks to QEMU. The patch that solves this issue is on this slide. The parameter allow memory relocate should have been set to false from the start, but the code paths have been missed. So this patch fixes the issue by setting this parameter to false. So now let's dive into the next bug. At some point in time, the Nvidia driver stopped working. This was a kind of error message we got on Linux. And on Windows, we got a blue screen of death. After searching what triggered this behavior, we found it was these patch files. I was not able to find a bug in it, so I guessed that Nvidia driver tried to do illegal specific calls that are now blocked. So let's try to patch the Nvidia driver, starting with Linux. Something interesting, after applying the patch files, the driver Nvidia crash, but the driver Nvidia open doesn't crash. I decided to try to compare those two drivers. The official installer from Nvidia contains those two drivers. Basically, each driver has a blob that is a core. Basically, each driver has a blob that is a driver core and a build chain to add a layer of communication with the kernel. So we have binary blobs, some makefile, and some C source code. Let's investigate the difference between the two drivers and how to add as much log as possible to understand what is going on. In the Nvidia blob, all the functions have been renamed to the kind of garbage we see on this slide. But in the Nvidia open blob, we have the original function name at the top of this slide. So I decided to try to compare those two blobs to rename the garbage name of the Nvidia driver to the correct name from the Nvidia open driver. And we repeated the same kind of operation for as much function as we can. Then I try to add as many logs as possible everywhere. I modified the make files, the Nvidia source code, the Nvidia binary blob, and the compilation chain. And I also added new prints in the Nvidia source code, as we can see on this slide. After quite some time, I ended up with this difference between the Nvidia driver at the top and the Nvidia open driver at the bottom. We see a 4-byte write done at offset 4 by the Nvidia driver. It is corresponding to a 2-byte write to the command field and a 2-byte write to the statue field. However, the statue field is a read-only field. The driver should never try to write to a read-only field. So we just found a bug in the Nvidia driver. It tried to write a read-only field. So let's patch the driver to forbid this call. We do that by modifying the Nvidia source code to forbid any 4-byte write starting at offset 4. And using this patch, the Nvidia driver now works correctly on Linux. So let's try to do the same thing for Windows. I tried to do that, but sadly it didn't work. So I needed to debug it more to understand what was going on. So we are going to need to go to the hardware abstraction layer. That is the thing that communicate with the GPU. So we are interested in everything that we either call all set bus data or all get bus data. That is the two main functions that will be used to communicate with the GPU. Using WinDBG, we determine that the driver crash before any call to set bus data. So we are only interested in get bus data calls. We see multiple functions that will call it with different parameters. We see a call using a double word, using a byte, using a double word at offset 0. And we will investigate more the call we will investigate the double word the get that start at offset 0. As you can see, there is a lot of functions that are calling the function we just saw before. So the dword call at offset 0. I courageously decided to stop the static analysis part and try to find what I am looking for using WinDBG. So I decided to print the call stack of the last call to get bus data before the driver crash. That way I know the problematic call. I knew that the call to get bus data are not required since in the Linux driver it works without doing anything related to that. So I decided to patch the Windows driver by modifying the conditional jump leading to the problematic function that we call the get bus data by replacing it with an unconditional jump to avoid this call. So we replaced the assembly code jump if 0 by an unconditional jump to avoid the problematic call. I repeated this operation a second time because the driver was still crashing. And this is my final script to patch the Nvidia driver. Applying that makes the Nvidia driver works. So now the Nvidia driver works on Windows and Linux. and we found at least one bug in the Nvidia driver. So the story in end here, or maybe not. In a non-hypervised context, a write call to a read-only field should be ignored by the graphical card. In a hypervised context, a write call to a read-only field should be blocked before it reaches the hardware. So the behavior should be the same, but it is not. Does trying to write to a read-only field trigger a hidden function in the graphical card? Or maybe there is a bug somewhere else too? So let's go deeper. First, many thanks to Mamarek. I probably would have given up without his help. I tried to draw some schematics to understand how a gaming virtual machine will be able to read and write a PCI configuration. It may be not exactly true, but that's how I understood it. So this is the process to create the gaming HVM as I understand it. Xen created DOM0. From DOM0, we ask Xen to create the gaming HVM. It creates a subdomain virtual machine with a QEMU inside, and QEMU creates the gaming HVM. There is many ways to communicate with a graphical card. For this bug, we will only be interested in reading and writing the PCI configuration space. So this is how I understand the road from gaming HVM to the hardware. I simplified it a bit by removing some code to Xen to make it more readable. When we want to read or write the PCI configuration space, it starts from the Nvidia driver in the gaming HVM. Then it goes to QEMU. QEMU will apply some logics and filter. Then the call goes to the PCI front driver of the subdom VM. Then the call goes to the PCI back driver of DOM0. Then the call goes to Xen, and then the call goes to the hardware. So we need to dig even deeper, and we need to look at all the steps we saw before to try to understand if something is doing something it should not do. Many hours later, I was able to collect the log on this site. It is a log to a single write call. First, at the top of the slide, it's at the layer of the gaming HVM. Below, it is at the layer of QEMU, and at the bottom, it's at the layer of Xen hypervisor. Some what the fuck later, I found that those lines are very interesting. We read the value before the write. It is something that we will call alpha. We try to write the same value alpha. We reread the value. It is not. It is now a different value. I redo that. We reread the value. It is now a value different from alpha. At this point, I smelled something like integer overflow. In the middle of this slide, we can see a code that triggers an integer overflow. It is a line that defines the mask variable. I confirmed the integer overflow bug with this code. Mask 1 corresponds to the original code. Mask 2 is when I replace the emule len value by the constant 4 without giving indication on the type. And mask 3 is when I specified that the constant 1 must be a 64-byte integer. So at the top, we see the original mask variable definition from the cube patch. And at the bottom, the same thing, but with the integer overflow bug fixed. So with this bug and another bug I fixed in the Xen hypervisor to support high frequency processor, I modified a grand total of 3 letters of code, and it took me months to do so. So I think I invented a new unit. It's a byte of patch per week. So we just saw a bug in the Nvidia driver and a bug in the QoS code. So let's conclude the hard technical part of this presentation. Yeah, multiple times I was close to giving up. Also, something I got in my mind multiple times. If you use Xen, please contribute because it feels a bit like that. So we saw one bug in Xen, one issue in Kemu, one bug in Cube, and one bug in the Nvidia driver. So now we'll talk. We'll talk a bit about the presentation from Deeplow from last year. In his ideal setup slide, he wished to have a GPU passthrough ready template. I tried to contribute by creating an installation script that will create this template. The basic idea is that we download the Arch Linux template from the community template repository. Then we install the GPU driver, Xorg, support to use the kernel provided by the virtual machine instead of the kernel provided by QoS, and etc. And configure everything that need to be configured, similar to the steps I described in my gaming HVM guide. The code is available here. However, I did little testing, so be careful. And I also added an option to configure DOM0, but be careful, it will not work on every setup and hardware, so please read the guide and documentation before using that. So now, let's configure our setup to play a game. We have two GPU, one integrated into in the processor, and a Nvidia card. One keyboard, one mouse, and one screen will be dedicated to gaming. Then we configure DOM0 and install a GPU passthrough ready template. I selected I selected to pass through the Nvidia card, and now we can just reboot the computer. We configure the BIOS to be sure to use the integrated GPU as the primary GPU. Then we start Cube and we can play a game. As a note about this video, the frame rate I have is around 40 to 60 frames per second. I say that because I know that when I try to do this presentation over network and GT, it will probably be laggy for you. But I wait a 5 seconds to so the video end, and we go to the next slide. It was supposed to have sound, but I didn't have time to properly configure my Pulse Audio settings, so you probably don't have the sound for this video. So I know it was probably laggy for you when I tried to do when I tried to do okay, I restart. It was probably laggy for you because of the presentation over GT and the network. But when I was running it on my computer, it was around 40 to 60 frames per second, and there was no issue. So let's go back to the wish mentioned by Deeplow. He wanted to do GPU pass-through without needing to have a dedicated keyboard, mouse, and screen, just like in the setup I just showed. It can be done by using VirtualGL, a solution mentioned by user Bamboo Dapen in a Cube forum. The disadvantage is that the performance is a bit slower than using a dedicated screen. In this setup, nothing will be dedicated for the gaming virtual machine. Also, I needed to specifically configure the variable LD library path to be /usr/lib, because using VGL run will modify this parameter and it will not work. So you need to specifically configure this variable when you use VGL run. So in the video that you probably see, I'm launching Final Fantasy XIV using VGL run. Same, it was supposed to have some sound, but I didn't manage to configure my Pulse Audio configuration correctly. It was just to show a bit how much time it needs to start, and that there is no complicated trick that you specifically need to launch the game once you have done all the previous steps. Same thing. It's maybe a bit laggy for you, but in this game, when I'm not recording, I have around 120 frames per second. It's really no issue at all. But I know that over the presentation and with the recording, it can be shown as a bit laggy, but it is not laggy when you play. Okay, love. So let's go to the next part. So now that we saw all the difficulty to set up GPU pass-through, how easy can it be to use? In my family, I am usually the IT guy. So I fix things and set up things. One of my family members who have no IT skill like to play an old multiplayer games. But time to time, the game breaks itself. And it is quite hard to fix. Just reinstalling the game from scratch is usually not enough. So I spend a lot of time to try to fix it. And it breaks again and again. So at some point, I decided to try to use CubeOS to solve this issue. So I installed CubeOS and created 2 custom scripts in the Cube desktop. You execute the script by clicking on the corresponding icon on the desktop. One icon to launch the gaming virtual machine, one icon to delete the virtual machine and redeploy a backup in a known working state. That's why when the time comes and the game breaks itself, I can say just click on the repair icon and it solves the issue. This setup worked for more than 2 years now, and it requires way less of my time than the previous Windows 10 setups. So yes, GPU pass-through can be very easy to use for a non-technical person. I want to thank quite a lot of people. Marek for giving me hint and explanation about how Cube and the Xen work. Jean from the Xen project for giving me hints and explanation about how Xen work. And CubeOS team, CubeOS contributor, Xen team contributor, because all of this work has been done on top of other people works. And also QEMU and Linux team and many, many other. That's all for me. I see that there was some questions in the Matrix channel, but I will try to read it and to answer it. And if you have any other question, don't hesitate to type it.
Thank you, Neo Wutran, for a great presentation. We in Berlin are preparing to ask questions, but first I have a question for Demi, who is connected to us through Jitsi. Maybe Demi has a question, please ask it. And we are getting ready to ask questions from Floor in Berlin.
Okay. So thank you for a great presentation, Marek here. And yeah, I have thank you also for all the great work, and it was really nice seeing this debugging, and you solve all this problem. Just one addition to that, I looked at that later. It was a patch that I wrote with this interior overflow, and it turns out that line was not needed at all. So I removed that patch and everything worked. Yeah, but I have a question about this VirtualGL. Is it actually needed? Because our GUI, XOR configuration driver inside the VM, will try to use real GPU for acceleration if it's there. So, and I think I've tried something like this without needing any extra VirtualGL.
Maybe it's something recent, but last time I checked, I actually needed to use VGL run, so VirtualGL, to be able to have a GPU acceleration for the game. If it was a really recent modification in the XOR configuration, like maybe 3 weeks ago, then I didn't tested it in the meantime.
Maybe it's specific for some game or a specific game or something, because yeah, I haven't tried game. I've tried Google Earth, which without GPU renders like 1 frame per 10 seconds, and with GPU it renders like very fluently. So I don't know, maybe something else. Thanks.
Thank you.
Hi there, Deeplow here. Thanks so much for all of the work. I don't know if you got the audio from the audience, but there was a lot of laughter, and I just wanted to share that. For me, there is like some as I was watching this, like I think at some point I decided like there was a convergence of a lot of different things. Like firstly, there was a certified hardware, which was a powerful modern desktop, and then there was some discussion in the forum about being able to run a GPU. So I just decided to combine both of them. Like I thought that I wouldn't be able to like get anything running because I mean, how many things can you combine that have little chance of actually succeeding, like all combined together, and actually did. And that was also built on top of your work. So thanks so much for that. It's not really a question, but more a description of what my experience, like going through your setups and excellent guides was. Like, I mean, I don't know too much about GPU stuff, and so it was pretty much like going blindfolded into a dungeon, trying for weekends and weekends. And I don't mean to say this in a bad manner. It was like excellent. In the end, I got something working. I didn't have any expectation of getting this working, but it was just excellent that at the end of several weekends trying all the setups, I even got like a riser card because I was plugging in the beefy GPU card so many times that I was afraid of breaking the motherboard. But yeah, it was excellent that I managed to get this working, and that's all thanks to you and all of the community members and like everybody who contributed to this. So thanks so much. And unfortunately, when I was trying to go into 4.2 land, I was having some challenges, and let's just say that the 4.1 SSD, which had all of the video editing stuff, all of the templates, was the same brand, the same model as the one for the 4.2, and I accidentally forgot to switch them. So I installed 4.2 over my 4.1 drive. So the videos are still in the making, and that's the reason why. But I'm very much looking forward to like finally being able to set this up on 4.2 and ideally having a template. So thanks so much.
Thank you. And don't hesitate to try this one. Maybe it will work. At least it worked for me.